Hello everyone, today we are going to talk about Boolean logic. Logic gates are fundamental building blocks of digital circuits. They are electronic devices or circuits that perform basic logical operations and, or, not, etc., on one or more binary inputs to produce a single binary output. These gates form the foundation for designing and constructing digital systems, such as computers and calculators. Each type of logic gate follows specific truth tables that define the relationship between input and output states. In the upcoming unit, we will introduce the following 6 different types of logic gates: NOT gate, AND gate, OR gate, NAND gate, NOR gate, exclusive OR gate. But before we delve into introducing these 6 logic gates, let's first discuss what truth tables are. Truth tables are used to trace the output from a logic gate or logic circuit. The NOT gate is the only logic gate with one input. The other 5 gates have 2 inputs. Although each logic gate can only have 1 or 2 inputs, the number of inputs to a logic circuit can be more than 2. For example, 3 inputs give a possible 8 binary combinations, and for 4 inputs, the number of possible binary combinations is 16. It is clear that the number of possible binary combinations is a multiple of the number 2 in every case. A NOT gate, or inverter, is a basic logic gate with one input and one output. It reverses the input signal. If the input is high, 1, the output is low, 0, and vice versa. Its symbol is often a triangle with a small circle at the input. In digital circuits, NOT gates are used for signal inversion and are fundamental in logic design for various applications. An AND gate is a fundamental logic gate with 2 or more inputs and 1 output. It produces a high output, 1, only when all of its inputs are high. Otherwise, it produces a low output, 0. In digital circuits, AND gates are used to implement logical conjunctions and are essential building blocks for various applications, such as data processing, arithmetic operations, and control logic. An OR gate is a basic logic gate with 2 or more inputs and 1 output. It produces a high output, 1, if at least one of its inputs is high. Otherwise, it produces a low output, 0. In digital circuits, OR gates are used to implement logical disjunctions and are crucial for combining multiple signals or conditions in various applications, such as decision-making circuits and data processing. A NAND gate is a logic gate with 2 or more inputs and 1 output. It produces a low output, 0, only when all of its inputs are high. Otherwise, it produces a high output, 1. It is essentially the inverse of an AND gate, hence its name, not AND. NAND gates are widely used in digital circuits for their versatility. They can be used to implement any other logic gate, and are essential in the design of various digital systems. A NOR gate is a logic gate with 2 or more inputs and 1 output. It produces a high output, 1, only when all of its inputs are low. Otherwise, it produces a low output, 0. NOR gates are essentially the inverse of OR gates, not OR. They are widely used in digital circuits for their versatility and are fundamental components in logic design, especially for implementing logical functions and control circuits. An XOR gate, or exclusive OR gate, is a logic gate with 2 inputs and 1 output. It produces a high output, 1, if the number of high inputs is odd. Otherwise, it produces a low output, 0. In other words, it outputs 1 when the inputs differ, and 0 when they are the same. XOR gates are essential in digital circuit design for various applications, such as arithmetic operations, data processing, and error detection. After learning the basic logic gates, let's look at a problem. Now, the problem is show why x and y both represent the same logic gate. First, we change the logic notation of x and y to the Boolean algebra. Before we begin solving the problem, let's introduce De Morgan's laws. De Morgan's laws are fundamental principles in logic that describe the relationship between negations, conjunctions, and disjunctions, or, of propositions. De Morgan's first law, the negation of a conjunction, and, is equivalent to the disjunction, or, of the negations of the individual propositions. De Morgan's second law, the negation of a disjunction, or, is equivalent to the conjunction, and, of the negations of the individual propositions. These laws are important tools in simplifying logical expressions and transforming them into equivalent forms, aiding in logical analysis and circuit design. Therefore, using De Morgan's laws, we can transform y into O or B, and not A or not B. Now we expand the parentheses using the distributive law. So, y is equivalent to a and not a, or a and not b, or b and not a, or b and not b. Since a and not a and b and not b are always false, we can simplify y to a and not b, or b and not a. Thus, we obtain that y is equivalent to x. Today we have learned about the basic logic gates and how to solve a problem using Boolean algebra. In the next video, we will look at some more advanced problems. See you next time. Bye-bye.